Alright, so this is the unit on forces by A.J. Eichmann. Forces are one of the most important concepts in physics. They basically determine the interaction between objects, and a force is defined as an influence tending to change the motion or body of a body or produce motion or stress in a stationary body. The magnitude of such an influence is often calculated by multiplying the mass of the body by its acceleration. That's Newton's second law, which we'll get to later. So useful units and variables that you should know are mu, which is the coefficient of friction, g, the gravitational constant, equal to 9.8, Fn, which is the normal force, Fg, which is the force of gravity, Ff, the force of friction, Ft, the force of tension, newtons, which are the measure of a force, meters per second, the measure of velocity, and meters per second squared, which is a measure of acceleration. And the general concepts in this unit are Newton's laws, gravity, the normal force, friction, free body diagrams, which are essential to almost every force problem, slopes, inclined planes, and two-body problems are just examples of problems that you'll encounter in the forces unit. So Newton's laws, there's three of them, and they also determine the interaction between objects. They explain the relationship between forces and an object's motion. The first law, an object in uniform motion will remain in uniform motion. An object at rest will remain at rest until acted upon by an external force. The second law is F equals ma, which is probably the most important one for this unit and the most used when solving force problems. The third law is for every force, there's an equal and opposite force. Gravity is also essential in most force problems, and the force of gravity is relative to the mass. It's 9.8 times the mass of the object, or if you don't want to write that, you can just use it by the letter G. It always points in the same direction, which is normally downward for most problems. The normal force is similar to gravity because it often acts perpendicular to gravity. It will always act perpendicular to the slope or whatever the object is resting on, because when one object pushes against the other, the normal force counteracts it to prevent the objects from being pushed into each other, and it has the same magnitude as the object getting pushed down. Friction acts in the opposite direction of an object in motion. The value of it is equal to the normal force times mu, which is the coefficient of friction. Mu is unique for every surface, and since it acts in the opposite direction of motion, it will normally slow down or eventually stop an object that's in motion on a surface. Free body diagrams are essential in basically all force problems. They're a way for you to get started and a way to show the forces that are acting on a project. It allows for the forces and their directions to be labeled and shown. This is just an example of an object that's not on a slope or inclined plane. It has the normal force, gravity, as a pushing force, and it has the force of friction acting on it, and that's all shown in the free body diagram. Slope or inclined plane problems are something that you'll most likely encounter if you're doing anything with forces, and that's because not everything's very simple with a object just on a flat surface. And when solving one of these, you'll often need to split the forces into their x and y components. This is done by considering one side of the force, the angled side, to be the hypotenuse of a right triangle, and using sine and cosine to determine the x and y components. Two-body problems are another problem that is often encountered in the forces unit. It, as expected, includes more than one body or object that's in the problem. This example is a modified Atwood machine, where as you can see there's two distinctly separate masses, one is m, one is 2m, and you would need to do a free body diagram, or FBD, for both of them to go about solving the problem. For this example problem that I chose one of the ones without any numbers in it that you just have to solve for the variables. A block of mass m is placed on a plane at an angle theta relative to the horizontal as shown. There's a coefficient of kinetic friction, mu of k, that acts as the block accelerates down the ramp by the acceleration of the mass m. So, as I said earlier, it has to be solved for a in terms of variables. So, first we have to do is start by creating a free body diagram. And you have the forces acting on it are the force of gravity acting downwards, the force of friction acting the opposite direction of the motion down the slope, the normal force, which is perpendicular to the slope. Since the object is moving down the slope, we need to break gravity down into its components to see what the force is bringing it downwards. And as I did here, we have to utilize F equals ma, or since that F is the sum of the forces, Fg minus F of F equals ma. The force of gravity must be isolated in its components, as I already said. Gravity is equal to mg sine A in the direction of the slope and mg cosine theta in the other direction. This leaves the problem as mg sine theta minus the force of friction equals ma, and that is mg sine theta because that is the component of gravity that is in the same direction as down the ramp. The force of friction, as discussed on the friction slide, is simply mu times the normal force. The normal force is equal to the force of gravity perpendicular to the slope, which is mg cosine theta. So, the force of friction is mu times mg cosine theta, so we have mg sine theta minus mu mg cosine theta is equal to ma. Now, there's m's in all of the terms, so they can simply cancel out, and you have the acceleration of the object is equal to g sine theta minus mu g cosine theta. And just to recap the unit as a whole, forces explain the actions and interactions of objects. If you need to solve a force problem, the first step always pretty much should be the creation of a free body diagram, because that makes it easy to visualize exactly what's going on, especially if the problem has a lot of words in it. It makes it much easier to see what you're working with and be able to solve it. Another very important thing in solving force problems is Newton's second law, because it allows you to take the mass and acceleration and connect it directly into the sum of the forces. As you can see in the example problem, it was very useful in being able to solve it. And for the third problem, if you're ever going to have a slope or incline plane problem, or just any problem where the forces aren't exactly, in the x and y direction, if they're going off at an angle, you have to remember that they can be broken into multiple components by use of sine and cosine to find the values in the x and y direction.